Okay, I'm not going to search for it right now, but so we're going to have two things. One thing we're going to prove is that the ghost state doesn't change the behavior of the system, and this is not that hard, right? Because the ghost handlers don't get to do anything aside from update ghost state. So we're definitely not going to add any additional behavior. We're going to preserve everything. But what's actually cool is that it turns out that every invariant that you can prove about the regular state of a system in the ghost transformer is also an invariant of the original system before it was wrapped. Right? So you don't even have to sort of add the ghost data to do the proof and then remove the ghost data. You can add the ghost data to do the proof and then just use a theorem, a regular Coq theorem, to get the fact that that proof is carried back to the original system's behavior. Right? So we really are just doing this for a proof. And this is something that we were pretty excited about because it means this notion of a verified system transformer, not only does it allow us to sort of modularize, to abstract out fault tolerance handling and reasoning, but also lets us extend Verity, right? As a verification framework, we can add new capabilities to new mechanisms for doing proofs just by implementing these verified system transformers. Okay, another idea that I wanted to briefly share with you all from this list of sort of proof engineering lessons learned was this notion of affinity lemmas. It always sounds like I'm saying infinity, but they're very finite. It's affinity. It's like when two things like each other, they have affinity. So one example is, suppose that I have something from my ghost state, E is in all entries. And when I prove the fact that E is in all entries, means that the term of that operation was positive, right? So this happened sometime after the first operation, right? It happened after the world began or whatever. To prove this, right, what I'm, the thing I have in my context is I have the fact that this event is in the actual state in my log, right? And the property holds for it there, and now I want to prove this. So it turns out that one way you might do this, instead of trying to grind it out for this proof, because we end up with a lot of things of this shape, right? We're actually going to use an affinity lemma instead. And what an affinity lemma says is it basically tells you relationships between parts of your state, right? That is, it lets you say things like, for any invariant that I can prove about entries in the actual log, those are also going to be true about entries in all entries, right? And so now I have this nice thing where anytime I want to prove something about all entries, if I already know about the log, then I get this fact for free, right? So this way of relating pieces of the state, especially for ghost state, turned out to be useful over and over. And in the CPP paper, there's several examples of these kinds of affinity lemmas that were very helpful. I think you can probably see these in a lot of different kinds of systems, and not just for ghost state either, right? Things like dirty bits, stuff like this, right? Where it's that state is really telling you something about other state. This idea, I think, is pretty useful. And there's some other examples here. The other thing that was sort of useful, that was kind of hard, is that, remember, handlers are atomic, right? So when we're trying to prove these things about the system, or reason about the handlers, that after every step we correctly reestablish our inductive invariance, those handlers are pretty big. They're doing this whole, they look at the state, they compare stuff, they count things, and sometimes within a handler, not everything is relevant to the property you're trying to prove. In fact, a lot of times maybe most of that handler for that given property, it just doesn't interact with the property at all and it totally preserves it. But we still have to reason about the full handler in every case. So one of the things we found was useful was, in our handler monads, we actually sort of decompose. That's why in Raft there were so many of those helper functions for the input and message handlers. We can sort of decompose things into sub-handlers, right? Now, this is also just nice for programming or whatever. But this alone doesn't sort of get us everything we want, right? So ideally what I'd like to do is I'd like to do something like prove, for some big class of inductive invariance, update state always preserves it. And prove that once about this sort of sub-handler. And then everywhere I do an update state call, I just get to use that for free, right? And then maybe after update state, different handlers do different things, and I'll have to deal with each of them individually. But I can sort of do that all for once. The problem is that we can't really talk about intermediate states of the system, right? In our semantics, what happens? You get an event, you run the full handler, right? And you spit another event back out. So another thing that we defined in Verity was this sort of intermediate reachability, right? So it's a finer grained network semantics for Raft specifically, right? So we did a system specific network semantics that's much finer grained. But it's not part of our spec, right? This is just a proof mechanism. What we show is that anything you can prove that's true about Raft in this finer grained semantics is true in the true network semantics where the full handler runs. And what we can do is instead of trying to prove that, if you know something's an invariant of the state of the world before and you're on the full handler and you get it, now you can split that up into smaller proofs about the invariance, right? So now I can show if it's true before, it'll still be true in this intermediate state and it'll reestablish itself again. Right? So this way of sort of using the structure of handlers to guide proofs was really useful. Now, of course, there's the things called program logics that allow you to use the syntax of programs to drive and guide proofs. One problem is that when we did Verity, there were no program logics for distributed systems. So I'll talk briefly about one that we published in January at Popl. So we didn't know how to do it yet. But even if we had the program logics at that point, I think this still might have been a good choice. Right? It's very flexible. Right? We don't have all the baggage of building the logic and having now you have to have some representation of programs, some syntax, and all of this. Right? We just have a very simple monad, and we have this intermediate reachability. And we get a lot. We get some of the benefits of having a program logic kind of for free.
And when you extract the implementation, you do it from the right or the left?
These are really the same thing. It's just that normally, in just regular Verity, right, you look at the whole handler. And so here what we've done is we sort of, when we prove it in Raft, we sort of reason about it on this side. And what we do is we prove that anything that's true about this is also true about this. And this is the thing, it's the real semantics that actually is run, that actually works, right? But this is nice for doing proofs.
So this isn't motivated by the thing you mentioned the other day, that if you've got crashes, they might come at inconvenient times in your implementation that aren't real states.
Exactly right. Yeah, so we don't have to worry about atomicity because we never run this, right? In fact, it's also just finer grained, so I think it would still be okay. But yeah. Yeah, that's right, actually, yeah. Okay, so this was something that was useful to do. Oh, and there's this, we'll talk a little bit about struct-tect, I think, in a little bit. Yeah. Okay, so we ended up doing this. 50,000 lines of cock is about a year and a half of LTAC hacking and a lot of very late nights. But it was very exciting because the creator of Raft gave us, grats on Twitter. That's what everybody wants, is to be Twitter famous. So it worked. Okay, so we were really happy with that. And then, people were sort of looking at the system, and we learned some more stuff after we got the proof done and published. So I want to take a little bit of time to talk about, some things that we'd still maybe like to do better and have started working on, but it'd be great to have more people pitching in with or thinking about stuff like that. So one problem is that, as we mentioned, right, yesterday, we assume that the handlers are actually executed atomically. And so these network semantics aren't just a model, it's also something that we need to try to ensure when we implement the shim, if we want to believe in these systems. And so, one example where we got some of this stuff wrong was, people found bugs about things we didn't promise to do correctly. So one example was this user found this issue that if you build a really small Raft cluster, the system never does anything. And the reason is that the one node cluster never is able to elect itself leader because it doesn't, get any responses. Right? And so it wasn't sort of making progress. And that's tricky because the way that we have things set up in Raft, or in Verity, remember, if we look at the network semantics, this is the same network semantics we were looking at yesterday, right? They all have this same structure where we talk about sets of reachable states, right? Let's find a small one that fits on the screen. Right, so here, all we do is we talk about this we have a potentially infinite set of reachable states, but when you prove this invariant, it's really just a safety property, right? You're proving that for any state you get in, nothing bad has happened. You can't really talk about easily here For every state I get to, from that point, in some finite amount of time into the future, I will have done a good thing. So one of the things we did, just as a first proof of concept, was take that lock server. So this is the same lock server we saw yesterday, but we extended our notions of sort of reachability to allow us to do liveness proofs. So if you go through this file, first we define the system. Let's find this. We added like another 1,000-something lines, but that actually lets us prove liveness of the lock server. And so when you grind through all of this, at the very end, you get this slightly nicer property, which is just that if a client requests the lock, then eventually it will get the lock. Eventually that lock will be held by that client, right? And this is actually, a lot of what we really want to do with distributed systems. We want to ensure that we will eventually provide service. Right? So this works for the lock server. It turns out, the lock server is already pretty darn small and simple. This proof wasn't completely trivial. Scaling this up to Raft, I think, would be a little bit tricky, but it's a start. We started looking at other sort of more general liveness reasoning. There are other frameworks. So like Iron Fleet has a proof of liveness for their version of multi-Paxos, which is another consensus protocol. Actually, I think there's been some other liveness work, but we started on trying to figure out how to do this in Verity with system transformers in general. So you have a composable way of getting these liveness results. Another thing that happened, though, is that other people looked for some bugs and published a paper about it, actually, which was interesting. So who here has heard of CSmith? Okay, so not quite everybody. So CSmith is this really cool project from Utah. And what they do is they built a machine, and it turns dollars and or CPU cycles into compiler bug reports, which is a neat thing to have, right? So the way that works is they cleverly generate random C programs, and they take that program, and they're careful to make sure it's deterministic and that it has no undefined behavior, and they compile it with a bunch of different C compilers, and then they run the resulting executables and compare the answers. And if they ever see somebody if they ever see like an output that disagrees with the majority, they flag that as likely being a compiler bug. They've actually been able to find thousands of bugs in hardened, mature compilers like GCC and LVM and ICC, and it's been really exciting. Now there is one compiler who just had way fewer bugs. Anybody want to guess which compiler that was? CompCert, right? And in particular, what happened was they did find some bugs in CompCert. They found bugs in the unverified parts. They found bugs in the parser. They found bugs in the pretty printers. They found bugs in, related to how the stuff that got spit out and then went into the assembler and made the assembler go, sort of made the assembler barf. But nobody's found any bugs in the verified components of CompCert, right? Which is not something you can say about, actually, I guess it is something. They also never found any bugs in the verified parts of GCC. But CompCert has a lot more verified parts, right? So basically, there was a team that wanted to do CSmith for distributed systems, and they wanted to. I think that some of these authors were sort of motivated by not wanting to have to do proofs, so they wanted to convince everybody that why do verification? These things still have bugs. But in fact, I think it's going to have the same effect that the work that CSmith had for CompCert, right? Which is that CSmith has ended up being a huge advertisement for formal verification, right? We have these big complex machines, these big complex programs that everybody depends on, these big C compilers. And we can automatically just generate tons of bug reports for them. And we can't do it for CompCert, right? Over years of testing, we found a handful of examples, and they're only in the TCB, they're only in the shim, they're only in the unverified parts. And so, I would like to, have, results of this paper tell the same story. So it turns out that they did find some bugs, but we were lucky, or, we did our homework, we ate our vegetables, we were virtuous, and, there weren't really any bugs in any verified components, right? So these issues that I think are in the Verity Raft repo now, these are all about things like, we used OCaml's serialization library to actually send messages, right? So remember, we have these handlers, right? And they spit out things that have the message type, and then somehow that has to go on the network. Well, a message in Coq is not a TCP packet-sized sequence of bytes, right? So somebody has to take that message and turn it into something that you can put onto the NIC and send out over the wire. And so for that, we used OCaml's Marshall library, and it turned out that there were some bad interactions with that. So one of the results of this is that we started this new library called Cheerios, which is yet another kind of verified serialization library. I think Benjamin Delaware was here, and he talked about Narcissus, which is another one, sort of really focused on sort of binary level protocols and stuff. So Cheerios is another alternative. The joke, right, is that it's serialization. I think I made that yesterday and got a groan. No, it doesn't get a groan. But this is a nice little project, right? It's all sort of type class based. You get a lot of stuff for free. But what's cool, right, is that this sits exactly in the verified system transformer story, right? So now you have some existing system, uses some message types that you would otherwise have just extracted and used unverified serialization for. If you have serializers and deserializers for that message type, you can just slap on another layer that, whenever you get a message, you deserialize it, then you pass it to the underlying handler. And whenever you want to send a message, it gets serialized and put on the network, right? And this is transparent to the underlying system. So it's exactly what a system transformer is designed to do. And now instead of running on in a sort of nice world, right, and its magical network that just knows how to send and receive values of some Coq inductive type, now we get guarantees for a more realistic network, right? A network that knows how to send and receive sequences of ASCII bytes, right? And there's a bunch of other stuff that we can do here, but this was kind of a nice example. Another thing that we've started thinking about more. So one of the main Verdi authors, Doug Woos, he's one of my students. I co-advise him with Mike Ernst and Tom Anderson, and Doug is really convinced by this point that Tom always makes, which is that if you actually want to develop a technique that's going to have impact, it's going to get adopted, it's going to change the world, the only way you're going to be able to pull that off is to teach it, right? So if the stuff we're talking about this past couple of weeks at DeepSpec only stays with the people in this room, right, we're never going to see the folks who are actually building the distributed systems we use, right? The engineers at Amazon, the engineers at Oracle, the engineers at Google and Microsoft and Facebook, right? The power company. Unless you guys are all going to go work at the power company, right? Folks at the power company aren't going to use it. So we need to be able to teach this stuff to get it out into the world so that it actually has impact. And I don't know if you've noticed, but learning how to use proof assistance is not super easy. It also turns out that learning how to build distributed systems is not super easy. People make a lot of money for knowing how to build distributed systems. And now our position with Verdi is, well, you should be able to use both distributed systems and proof assistance and do things this way, right? And that's a really tough proposition, right? How is that going to work, right? You're asking a lot of the developer. So Doug's been really interested in this problem, and he's actually started teaching the undergraduate distributed systems class, trying to figure out how we can bring the ideas from Verdi and the techniques and these ways of building and thinking about systems into the classroom, so that hopefully one day we can have the folks at the power utility who are writing the distributed systems use Verdi or derivative techniques that were inspired by it. And one of the cool things that Doug has built that I actually really like is a visualizer, right? So you can actually, this is a video of using, it's called Oddity. And it actually lets you, have a system that you can reason about running dynamically in the browser. And what's cool about it is that you can sort of inspect the state. It plays for a little while. I think Doug sort of clicks around and shows you can sort of look inside of the state of the node. And you can see the state of the network, you know which messages are for which node. You can deliver it, deliver messages. See if I don't know if I can jump. Can you control videos while it's going? Yes. So you can see the messages get delivered. But one of the things I really like about it is that you can also, you can sort of like go back and see what the world used to look like, and you can jump back into history. But then you can also time travel. So I can, here, I can see what things looked like at this time. I can drop a message, though, which is not what I originally did in that state, right? So I can fork, and I can see this alternate way of having the system evolve. And the idea is that for these undergrads, this will be very helpful for realizing there's a lot of possible behavior